Hey, this one's a bit different. Um, if you don't know, I have gotten basically all of my ideas for videos from the GHP program, which is a program I attended this past summer where I learned a ton about mathematics, including like number theory, knot theory, combinatorial game theory, all that good stuff. There is a professor up there named Bill Shilido. I think he teaches at Oglethorpe University, and he's working on his PhD. So he is a big fan of the concept of dividing by zero. He has his own website and everything. I'll show you later. And he is also a big fan of projective geometry because this is what makes that possible. So yeah, I'll probably try to link his I'll try to link his YouTube channel and everything in the description. But yeah, this is just an insight into some projective geometry topics. And I'm not an expert on this, obviously. Whenever I share videos and everything, I share what I know about the topic. So just keep that in mind and take everything with a grain of salt. And some of this stuff I came up with myself, and it's just food for thought. But yeah, here we go. So projective geometry is basically um, it's basically what it sounds like. You're projecting a shape or a plane or a space, and you're looking at it in a different way, so that in a way that you've never looked at it before, basically, so that it makes some different things possible. So imagine like an ocean, right? We have this big plane of just blue. Imagine, let's succumb to the what's it called? Slipping my mind. The gosh, sorry. The whatever it's called you when something's conspiracy. Yes, I can't think of words. I'm sorry. I'm a math, not English. Um, let's succumb to the conspiracy that the Earth is flat really quick. Let's not get too hasty. It's not, but let's just say that the Earth is infinitely flat. Now, obviously, it wouldn't have a horizon, but we're gonna say it does. Um, so this is a horizon up here. Since the Earth extends infinitely, right, in this hypothetical conspiratorial flat Earth, since it extends infinitely, at this point, this is the end of infinity technically. So this is infinity. I mean, like this is like we can see infinity, and that's what we call a point at infinity because I mean we can see it, we can put a point on it. So now I want you to imagine a number line, right? Just a normal number line and extends 1, 2, 3 in that direction, 1, 2, 3 in that direction, positive, negative, all the good stuff that you learned back in elementary school, primary school, whenever you learned about number lines. And sorry, this is kind of hasty. I kind of threw this all together last second because I had this idea. But now I want you to throw this out the window and instead think of a more condensed number line, a number line that can fit every possible real number in a confined space. And to do that, we're just gonna we're gonna pull a little trick and keep continuously getting larger and larger until we hit a point that is infinity. And we're gonna see that we're gonna see how that works in just a second. This seems kind of random right now, but we're gonna see how it works in just a second. But with the idea of projective geometry, you can kind of imagine like a road, like a road extending off into the distance into a horizon, where that road kind of it meets the horizon at a point. Imagine that as a point at infinity. This is a road, and it's extending into the horizon right here. This is infinity right here. And same thing over here. This is a road. It's leading into the horizon, which is a point at infinity. So now we're actually going to, hold on, if I can remember the keybind, Shift L, yes. We're actually going to try and link negative infinity and infinity to make a circle. And again, this seems kind of random right now, but it will make sense in a minute. And you might think, how the heck do we connect negative infinity and infinity? That doesn't make any sense. But let's just try it and see what happens. So we have a circle, and we have 0 on the bottom. It goes up in quarters. It goes 1/2, 1, 2, and then whatever this is up here. This is infinity and negative infinity combined. So what do we even call this? Like, I mean, we've met them up. They're the same thing now. What do we call this? Well, we actually end up calling this unsigned infinity with this little tilde on top. That was a horrible circle. This little tilde on top. Still a horrible circle, but you get the idea. Because it can't really be both positive and negative, so we just say that it's both. Or neither, if you will. That's why it's called unsigned. So you'll notice that the way that we set this number line up, it's gonna make more sense now. The reciprocal of each number is reflected over this horizontal line going through it. So we have 1 in the middle, right? So the reciprocal of 1 is 1. If we reflect across this axis, I mean, it's still 1. If we reflect 1/2 across this axis, it's 2. That's the reciprocals. So if we have like 4 right here, we have 1/4 down here. These are reflected across this axis. That makes sense. We have 1/9 right here. We have 9 up here. These are reflected over that axis. So now I think you'll start to notice where I'm going with this. We have 0. If we reflect 0 across this axis and get its reciprocal, in other words, 1 divided by 0, we get unsigned infinity. And so we get this idea that 1 divided by 0 is equal to unsigned infinity. And this is kind of a weird topic, and it doesn't really make much sense. It doesn't really make much sense objectively when you start thinking about it. But once you actually do get into it, it makes sense. I mean, imagine the graph of 1 over x, right? You have at 0, which is, I mean, this is the graph of 1 over x. This is 1 divided by 0, right? It goes to both positive infinity and negative infinity at the same point. So, I mean, it's going both directions. I mean, it's going to both positive infinity and negative infinity. So it kind of makes sense that unsigned infinity would be your answer here. But this kind of got me thinking, looking at this plane, and this is where the weird stuff that I kind of came up with comes in. So again, take this with a large grain of salt, because I came up with this on the fly basically because I thought it was an interesting little food for thought. We have this Cartesian plane, right? And we have positive infinity up there and negative infinity way down there. So what happens if we connect those like we did with the number line? Well, I mean, let's just look at a plane and condense it down in both dimensions the same way we did with the number line. So we have in this direction the 1/2, 1, 2, and then the infinity in the x direction, and then negative infinity in the x direction, infinity in the y direction, and negative infinity in the y direction. So we have a little compact square. Oh my gosh, I'm so sorry. We have this little compact square that makes up our Cartesian plane. That went straight through the infinity, whatever. This is the entire infinite plane, basically stuck in the same place. Again, imagine kind of a horizon going off, a road going off into a horizon at each of these. Like if we have a little road here, that's kind of extending off into the horizon. That's terrible, but you get the idea. A road kind of going into the horizon, you know, big sunset right here. I'm getting distracted. I'm just drawing at this point. Yeah. Again, just to hammer home what this actually, like how we can actually put infinity at a point. This right here is infinity. So imagine we do the exact same thing we did with the number line, right? Kind of make a circle with it. But now we're two-dimensional, so how would that work? Well, let's take it one step at a time. Let's bend it. Imagine this is a sheet of paper. Let's take the ends of this sheet of paper, connect them in the x direction. So we're going to make a cylinder, right? And if you notice, I highlighted the x-axis red and the y-axis blue just to keep track of it. So we bend it. We now have a cylinder. We got the x-axis right here. This is the 0 point right here. And we have, you know, the infinity y points, the negative infinity y point. Well, technically these are lines because all of this is negative infinity in the y direction. All of this is infinity in the y direction. And then we have unsigned infinity in the x direction, which is this invisible line back here behind the cylinder because negative infinity and positive infinity met at that line. So now, oh, I'm so sorry. You just got a glimpse of absolute horror. That is what happens when you connect these circles on the top and bottom to make unsigned infinity in the y direction, which doesn't sound very intuitive at first. You know, how the heck do you connect the two ends of a cylinder? I mean, just picture it in your head. You have a imagine a slinky. Yes, that's a good analogy here. Imagine a slinky, right? You have it all compacted up. Imagine uh pulling apart the slinky, right? And connecting the two ends of the slinky together to make this kind of donut shape. I'm sure many of us have done this in the past. I know I have because I'm a nerd. And you connect the two ends of the slinky right here to make this donut. And that's exactly what we're doing right here. You see, we still have that cylinder shape. It's just the two ends are connected right here, which is our unsigned infinity in the y direction. And we still have our unsigned infinity in the x direction on this inner circle right here. And here's our 0 point right here. This is the x-axis. This is the y-axis. So, and this y-axis actually, it's funny because the y direction is any circle on this torus. I don't know. Torus, projecting things onto a torus is very interesting and very weird. So we have this 0, 0 point, right? But you'll notice we also have, in addition to the x and y axes, we now have this unsigned infinity, this unsigned x infinity axis, and this unsigned y infinity axis. And you'll notice that they come together at a point. I don't know what to call this. I'm going to be completely honest. I ended up opting for unsigned XY infinity because I genuinely have no idea what to do with this. But I mean, it's just really cool to me that you can have the the x infinity, the all of the infinities basically all coming together like this. I mean, you have both positive and negative infinity in the x direction, and then you have both positive and negative infinity in the y direction, and somehow all four of those infinities are meeting at one point. I mean, this is four infinities in one right here. Like every single infinity version is coming together right here. Those four edges of the Cartesian plane, this guy, this guy, this guy, and this guy, all of them are meeting right here. I mean, it's so weird. Like it's just it's I mean, it's astounding to me, honestly, that you can do things like this. Which is this is part of the reason I love math, because this doesn't really, I don't really know what to do with this, honestly. But the fact that I have no idea what the heck this means and that this can be looked into just says it excites me, you know? It makes me like wonder what can we do with this in the future? Which, if you haven't noticed by now, this doesn't really have any practical applications. Anything involving infinity doesn't really have many practical applications. But at the end of the day, it's just interest and excitement is what motivates people to do a lot of things. You know, it may not have a lot of practicality, it may not make a lot of sense, but when you really dig into it, and if you're really passionate about mathematics, then you end up discovering things that, again, don't really make any sense to people that don't have a hyper specific hobby, but that are super interesting to you. And I mean, that's why we have what we call recreational math. We have this math that we do for fun, that we do just to figure out stuff. um like that whole branch of math is just basically a whole thought process. It's like philosophy, why do we do anything? Why do we I'm getting way too deep into this. Point being, it's very interesting, and I think this is the reason that a lot of people like math. Now, I'm actually gonna X out of the presentation for the first time in one of these videos. Yes, I know, it's amazing. You see the animations I did. This is this is what I look this is where I looked up unsigned infinity, and some of the first images that come up on the board are literally the website that my GHP professor made. I'm so sorry. This is bugging out like crazy. But yeah, this is his website. Like this is literally the guy. This is my GHP professor that made this right here, and he. I mean, he explains this perfectly. Like he goes through basic division rules, how it wouldn't really make sense to divide by zero. You know what happens when you approach zero. I mean, just a bunch of really cool, interesting stuff. He gets into projective geometry. He gets into why positive infinity and negative infinity can actually meet at the same point. What unsigned infinity is, and finally this conclusion, which also tells us this: mind equals blown. This guy is amazing. I love him, and he is. You can tell he's super passionate about this stuff. Again, I'll link everything in the description probably. Um, I also found when I was looking at if anybody had done this before with the Taurus, I did find somebody that put the on I did put find somebody on Reddit in r/Desmos that put the entirety of the infinite plane on the surface of a torus, which is basically exactly what I did right here. But they actually did this in Desmos, which I have it pulled up right here. And you can like move a point around to see where it's actually mapped to. See this point on the torus is mapped to this guy right here. You can move it around and see, it's going off into the distance. And then you can also move this guy, and see where it's going. I don't know. It's very cool. It's very cool. This is just a big nerd out for me right now. But you can also see that, you can also see, I mean, they said the top is infinity and the bottom is zero. The top right here, you can see it's infinity because, I mean, if you increase this by like a ton, like you keep going up, it never actually touches that point. It looks like it's touching it. It's not. It's just super close to it. And I can't really zoom in because it's going to kill the torus. Yeah. But it's just, I mean, this stuff is super interesting, and this is why this is part of the reason I love math. It's just because of stupid stuff like this that makes no sense to a lot of people, but it's just really, it's crazy. Um, anyways, yeah, that's about it. Um, I hope you guys have a good day, and peace.